Every day, millions of people travel by air. So how do airlines make sure that every aircraft has its full complement of staff and keep track of and coordinate a very large number of moving parts? The answer lies in an area of mathematics which investigates networks. It's called operations research. Airlines use operations research and networks to come up with clever shortcuts to find the best solution.
So this was designed originally for crewing.
Operations research was originally used to optimize military operations, but these days it's applied to all sorts of industries.
It's optimization problems where you're trying to minimize the cost or get the maximum value out of a fixed budget. It's used in many transport applications, it's used a lot in the airline industry, and it's used to optimise the layout of optical fibre networks, the allocation of organ transplants, all sorts of crazy things all over the world. And behind many of the things we use these days lies some sort of operations research algorithm. The applications are enormous.
Back in the 18th century, the 7 bridges in the city of Königsberg became famous due to a clever mathematician called Leonhard Euler. Everyone wanted to know that if they started at some point in the city, could they cross each of the 7 bridges once and only once and return to the starting point? Euler worked out that it couldn't be done and why it couldn't be done. This represented the beginning of graph theory. A graph is another name for a network. For mathematicians, a network is made up of nodes, the locations in the network, and arcs, the connections between nodes. For airline routes, nodes are airports at a particular time, and arcs, or edges, are flights, the connections between airports.
Nodes are not just locations. It's a location at a time. So a collection of nodes and directed arcs is what we'd refer to as a directed graph. And in the airline industry, we're nearly always dealing with directed graphs because of this time dimension. When we have a graph, we will have weights associated with it, and those weights can represent the cost of carrying things on those arcs, the time that the arc takes to travel. The capacity of an arc would normally be the number of passengers that can be carried on that arc. And this is one of the great things about graph theory. We can take this abstract theoretical concept and use it in so many practical ways.
Consider the problem of moving an individual passenger or parcel from their origin to their destination. We might want to know the quickest journey or the cheapest journey. To do this, we would use what is known as a shortest path algorithm. These algorithms have existed since the 1950s, and we use them every day when we use a public transport planning website to calculate the best public transport journey between 2 locations, or our GPS to calculate the shortest travel time through a network. Here, the nodes are the intersections, and the arcs are the roads that connect these intersections, and the cost of traversing an arc is the travel time on the road.
There's probably a Dijkstra's shortest path algorithm solved at least every second on the planet now, and probably hundreds per second. The airlines want to design their timetable so as to be able to move as many people as efficiently as possible, and to move those people where the demand is, also where the ability to pay is, so they're trying to maximise their revenue in some sense. It creates a whole lot of problems of its own because it creates these huge airports with lots of congestion. And overall, you can think of this as a particular graph theory problem known as a maximum flow problem. And these problems can be solved relatively quickly with operations research techniques. And a minimum cost flow is when you have a lot of things to move through a network, and the capacity is forcing you to move things away from their cheapest path.
The optimization problem of crew scheduling is first represented as a directed graph. Airlines are also faced with numerous operational problems, like scheduling crews, changes to the roster, frequency and capacity of flights, regular maintenance, fuel and air traffic control charges, and avoiding bad weather and war zones. The airline must quickly build a plan to get things back on track. For many of these problems, a technique known as linear programming is used to optimize amounts. It could be to minimize or to maximize. Common amounts to optimize are costs or profits.
The mathematics, the way they work, guarantee that the answer that we'll get out of the linear programming problem won't have any fractions in it. That's a good thing because we don't want to move half a person. That person would be pretty upset. So, however, if we are going to get fractions out, then we have to resort to using linear and integer programming techniques, and in particular using a very famous algorithm known as the simplex algorithm to solve those problems.
In integer linear programming, binary or decision variables are often used. These variables take values 1 or 0.
In a lot of problems, the variables are integers, and in particular they're 0 or 1. Should a certain connection be turned on or off? Should a particular crew member travel on this arc or not? It's a decision that you can turn on or off. When all these disruptions happen and you need to recover, operations research really comes into its own. We need to increase our capacity that more and more people know what operations research can do, because the more people who know what the possibilities are, the more people will be asking the right questions about can we do this better.